All right, we're going to wrap up our chapter on matrices with section 7.8, applications of matrices and determinants. So this is really looking at how can we use the matrix along with determinants to do a few problems we've actually already covered in the earlier in the year. So early in the year, you might recall a problem where you were given 3 vertices and you had to find the area. Well, we did that earlier in the year. I won't go through how we used to do it. What I will go through is our new way using a matrix. So essentially, these 3 coordinates go in the first 3 rows, all right? And then your last row is filled with all ones. And if you do that, so you set up this 3 by 3 matrix, then you can find the area of a triangle as plus or minus. Now, obviously, area has to be positive, but the determinant could be positive or negative. So that's why this plus or minus is here. It's plus or minus 1/2 the determinant of A. All right, and again, that plus or minus is there so that your answer must always come out positive. All right, so why don't you put this into your notes, and on the next slide, we will do an example. So it says find the area of a triangle whose vertices are 1, 0, 2, 2, and 4, 3. So the matrix I'm going to set up 2, 2, 4, 3. The last row is always ones. So what I do here is I now take the determinant of this matrix. It's going to be 1/2. If I call this A, it's going to be plus or minus 1/2 the determinant of A. So in the last chapter we went over determinants. Calculating a determinant is measured by doing cofactors. So if I think and I eliminate my first row and my first column. So I'm going to use the first row to calculate this matrix. So it's going to be, so to get the determinant of A, it's going to be 1 times the cofactor of entry 1, 1, plus 0 times the cofactor of row 1, column 2, plus 1 times the cofactor of row 1, column 3. Now I know this piece is going to be 0, so I don't have to worry about it. And all I'm going to do now is calculate the cofactor here. So if I'm calculating the cofactor, I eliminate this row and then my first row, and I'm really looking at this box right here, and I'm taking the determinant. So that's 2 minus 3, so 2 times 1 is 2, minus 3 times 1 is, so that's negative 1, so it's going to be 1 times negative 1, plus, and now I'm looking over here, this is where the 1 comes from, and then my last cofactor is found by eliminating these 2 and really focusing on this, and I get 6 minus 8, and that's going to be negative 2. So I total this up, negative 1 plus negative 2. That's my determinant. Again, it's not the area of my triangle. It's going to be 1/2 times negative 3, and of course I get negative 3 over 2, but remember that plus or minus that's in front of the formula means I'm going to record this area as 3 over 2 because area is always positive. You should know from determinants you did not have to use this top row to calculate determinant, but I chose it because it had a 0 in that row. It makes calculating the determinant a little bit easier. So, and then obviously, just remember when you're using cofactors, had there been any other number here, you would have had a sign change with that cofactor being in a place where the sum plus the sum of the rows and columns was odd. But I'm sure we'll go over other examples in the homework. All right, so another application of determinants is collinear points, all right? And it works with a very similar setup. If I give you 3 points, again, just like in the last problem with the triangles, you had 3 points. You set it up exactly the same way. You put your first point, your second point, and your third point, and then your last row is all ones. Well, here, if the determinant is 0, then you know you have the points are collinear. And what that's saying is the area of these 3 points is 0. And the only way that's going to happen is if the 3 points are in an exactly straight line. Because if they're not in a straight line, it's going to be a triangle that has some sort of an area. So it's kind of an extension of the last problem. So again, it really works exactly the same way. If I set up my matrix, and I'm going to put all ones in the last row to figure out, are these points collinear? If I call this matrix A, I'm really concerned about what is the determinant of A. So To do this, maybe this time, it looks like this second row is going to be pretty easy to use for a determinant. So to do that, I would have to take the 1 times the cofactor of row 2, column 1, plus 1 times the cofactor of row 2, column 2, plus 1 times the cofactor of row 2, column 3. So let's do it. If I'm taking the cofactor of this position, I am crossing out the first row and the second row in the first column, and it leaves me with negative 2 times 1, so that's negative 2 times 1, that's negative 2, minus 5 times 1, so it's going to be negative 7. I have to remember a sign change, so that's going to make this the opposite of negative 7, so it's really going to be positive 7, plus, now I'm doing the cofactor of row 2, column 2, so that's going to be negative 2 times 1, that's negative 2, minus 1 times 7, so that's going to be negative 9. That sign stays exactly the same because the cofactor is even. And last but not least, taking the cofactor here, I'll cross out, and I do negative 2 times 5, that's negative 10, minus negative 14, so here the minus, the negative, that's really plus 14, so it's negative 10 plus 14. I'm getting positive 4, remembering to do a sign change, and what I get here is 7 plus negative 9 minus 4 equals, that's going to be negative 6. So the conclusion we can make here is that these points are not collinear. They do not form a straight line. They are not collinear. And in fact, if I wanted you to, so those 3 points make a triangle, and the area of that triangle is going to be 3. And the way I'm doing that is half of negative 6 is negative 3, and of course area is always positive. It would be the exact same answer. So had this turned out to be a 0 right here, then I would have been able to say, that this has a, that these 3 points are collinear. All right, so the last part that I want to talk about with you, this is Kramer's rule, and Kramer's rule is a little bit tricky. I'll probably show you this in class, but I want to explain a little bit so you get some notes on it. What Kramer's rule is essentially another way to use a matrix to solve a system. So right now we have the row reducing, the back substitution. That's worked for a lot of 3x3 matrices. So if you have a matrix that has a non-zero determinant, all right, then you can come up with the, so let's say it's a 3x3, so 3x3 matrix for ease of use. You actually could calculate the 3 coordinates x, y, and z by doing, and again these bars mean the determinant of A1, and I'll talk about A1 in a second, divided by the determinant of A, and I'll talk about the difference between A and A1. But essentially, you could calculate x, y, and z just by doing determinants. And the tricky part is, well, what's the difference between matrix A1 and matrix A? Well, matrix A is your standard matrix, all right? That's the one you've always made, all right? The trick, so you're gonna, that's the coefficient matrix that you've solved, that you've used in every row reducing, all right? The 3x3 portion, all right? A1 takes out the first row of, so I hope we have a good understanding of what A is. What A1 does is it takes out the first row and replaces it with what's after the equal sign in your matrix. And that's called the augmented column. All right, so the augmented column, that's what's after the equal sign. All right. All right, and then A2 is the same thing. You take out the, so to get matrix A2, you take out the middle column and you replace it with the column that is after the equal sign, the augmented piece of the matrix. So I'll let you, and then A3 goes the same way with the third column. I'll let you get this in your notes. I hope I haven't confused you too much. We will use Kramer's rule to solve this 2x2 to start class next time I see you.